Welcome back. We're going to spend some time talking about sorting. In the previous lecture, we talked about searching. How do you find something in a database based on name, social security number, address, or any other identifying information? And we saw linear search and binary search. Now remember, for binary search, where we kept dividing the list that we were searching for in half, looking either to the left or to the right, depending on what we were looking for being less than or greater than a midway point, that assumed that the list was sorted. And so what we're going to do is talk about sorting. So sorting is important for lots of reasons. Binary search we've already seen, and for a number of other reasons that we'll see going forward. And so what we're going to do is talk about a series of different sorting algorithms, and then we're going to do the runtime analysis using big O notation. So we get two things for one. We see how these different sorting algorithms work, and we start to refine and hone our skill and ability to compute runtime complexity using big O notation. So first sorting algorithm is going to be selection sort. Okay, so throughout all of this, we'll work with a simple list. And for now, we'll just put integers in here, but this can be anything that has a natural ordering to it. It could be alphanumeric, it could be anything, but just for simplicity, we'll deal with these simple lists with just a bunch of integers in it. And our job is to sort it, let's say, in increasing order. Now here you'll notice that all the numbers are consecutive, 1, 2, 3, 4, 5, 6. Obviously they don't have to do that. I've done that just to make it sort of a little easy to see where everything should go, but obviously there can be gaps. And to keep things simple, let's assume there's no duplication. So there's only 1, 5, 1, 3, 1, 2, etc. Okay, so selection sort says, let's do the algorithm, and then we'll do the runtime complexity. Step 1, find the smallest item in the list and swap it into the 0th position. Remember, lists are indexed on 0, 1, 2, 3, 4, 5. So the indices are from 0 to the length of the list minus 1. So it's saying find the smallest element in the list and swap it into the first position. So I'm going to go through here. There's the smallest item in the list, and so I'm going to swap it with that item. So it'll look like this. Why am I doing that? Well, if it's the smallest item in the list, it belongs in the first position. Okay? So I now know that that number is in the right position because it's the smallest element in the list. Step 2 of the algorithm. Find the second smallest item in the list and swap it into position 1. The other way to say this is find the smallest element in this part of the list, ignoring the element in the 0th index. So find the smallest element in here, that's a 2, swap it into index 1. Yeah, good. Now, this part of the list is sorted, guaranteed, because this was the smallest, second smallest, and now we have to do the same thing over and over again. So, find the third smallest element in what is left over here. So that, of course, is 3. We're going to swap that into index 2, and then we're going to repeat over and over and over again until we get to the very end. So every time we look at the first step, we look at the whole list, find the smallest element. The second step, we looked at everything in the list except the first element. The third step is we look at everything in the list except the first 2 elements, and so on and so forth. And eventually we get to the very end, and of course this will be guaranteed to be the largest element in the list because we keep finding the smallest, the smallest, the smallest element. Okay, that is selection sort. And I think you can see that it's correct. It's sort of logical and easy to implement. So here's a good exercise for you. I'm going to show you the code for this in a minute, but this would be a good exercise is write selection sort. So selection sort should take as input a list. Using that algorithm that I just described should sort the list in place. So you can modify the list. You don't have to create a new list. So when we come back in the second segment, I'm going to show you my Python code for doing that. And then we're going to do the runtime analysis of that. So we'll be back in a few minutes with that.